Hello there, and welcome to a quiet exploration of one of the greatest mysteries we face. Tonight, we're going to drift through space in our minds, not across its vast emptiness, but through the questions that it raises about distance, about silence, and about the possibility that we might never find the civilizations we suspect are out there. The universe is incomprehensibly large, and the distances between stars are so enormous that they reshape everything we think we know about communication, travel, and whether life anywhere else could ever truly reach us, or we could ever reach them. For years, scientists have searched the night sky with radio telescopes, listening for signals that might prove we are not alone. Yet the silence persists, strange and profound, and the more we learn about the cosmos, the more we begin to understand that this silence might not be an accident or a mystery with a simple answer. It might be the natural result of the brutal mathematics of space itself. Distance might be the greatest barrier that separates civilizations in the universe, not hostile intentions, not self-destruction, not the rarity of life itself, but simply the almost incomprehensible gulf that stretches between the stars. As we move through this investigation, you'll come to see how profoundly space isolates worlds from one another, how the laws of physics themselves conspire to keep civilizations apart, and why the search for alien life might be a search for something that is fundamentally impossible to find. We live in an era of remarkable scientific achievement, where we have mapped the cosmos, discovered thousands of worlds orbiting distant stars, and extended our senses across light years of space using instruments of extraordinary sensitivity. And yet, for all our progress, we find ourselves confronted by a silence that no technology seems able to penetrate. This is the paradox that defines our cosmic perspective. We have become sophisticated enough to know what we should be looking for, yet our observations tell us that whatever we are looking for, it is not here. For now, just breathe and allow your mind to expand into the scale we're about to explore together. To truly understand this problem, we must first grasp the scale of distances we're dealing with. A light year represents the distance light travels in 1 year, which equals approximately 6 trillion miles, or roughly 63,000 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. These numbers exist almost beyond human comprehension. If we scale down the Earth-Sun distance to just 1 meter, the distance to our nearest star system, Alpha Centauri, would be 276 kilometers away. This simple reduction helps illustrate something that bare numbers cannot quite capture. The cosmic neighborhood is incomprehensibly vast. Even our nearest stellar neighbor is impossibly distant by any human standard. The actual distance to Alpha Centauri is about 4.3 light-years away, which translates to roughly 25 trillion miles. At the speed of our fastest spacecraft, Voyager 1, reaching Alpha Centauri would require approximately 76,000 years of travel time. To place this in historical perspective, if Ice Age humans had launched a starship to Alpha Centauri at Voyager's speed when the last Ice Age ended 11,000 years ago, that spacecraft would still be less than 1/6 of the way through its journey today. Voyager itself will not reach the distance of Alpha Centauri for another 70,000 years, traveling through the dark void at roughly 17,600 times slower than the speed of light. These staggering timescales reveal something fundamental about the cosmos. Any civilization attempting to traverse the stars would face challenges that dwarf the entire recorded history of human civilization. The distances are not merely large, they are so enormous that they fundamentally reshape what is possible for any biological entity. Consider that our fastest speed, ACE probe, launched with the accumulated knowledge of a technologically advanced civilization, would still require 70 millennia to reach the nearest star. A medieval human traveling at the speed of a horse could cover the distance from Europe to Asia in a matter of months. Modern commercial aircraft can circle the Earth in roughly 2 days. Yet our most advanced spacecraft cannot meaningfully traverse even the local stellar neighborhood in any time span that matters to human civilization. The observable universe contains billions of galaxies, each with billions of stars, and the space between them operates according to rules that make human expansion into the cosmos seem fundamentally impossible. The scale is so vast that it creates a kind of cosmic perspective. Every star system, no marshes for many a company, planets, engineers, and Zhenjing, Begersen, and Jev, at how distant it appears from Earth, is simultaneously surrounded by distances so immense that everything feels isolated. The universe is simultaneously crowded with billions of potential worlds and absolutely empty, because those worlds are separated by gulfs that dwarf comprehension. This brings us to one of the most devastating physical limitations facing any attempt at connection across the stars. Light itself travels at an absolute maximum speed, constrained by the fabric of space-time itself, and this creates an insurmountable barrier when we try to send messages across the cosmic void. Radio signals, which have been the primary focus of SETI, the search for extraterrestrial intelligence, experience what scientists call free space loss as they travel outward from their source. Imagine a radio transmission expanding outward like an ever-growing sphere. As the sphere grows larger, its surface area increases exponentially, and the same amount of signal energy must spread across an increasingly larger area. Conservation of energy demands that the strength of the signal in any given location must decrease as the area it covers grows. This is not due to any medium absorbing the signal or any physical obstruction, but purely a mathematical consequence of spherical geometry. The power of a radio frequency signal is inversely proportional to the square of the distance it travels. This means that if you double the distance a signal must travel, the signal strength drops to 1/4 its original power. Calculations from decades of radio astronomy research indicate that radio signals from civilizations at our technological level would become indistinguishable from background cosmic noise at distances beyond about 5 light-years. This is profoundly limiting because it means that even a civilization using our current level of technology to broadcast its existence would essentially be sending messages into the cosmic void with virtually no chance of detection beyond a handful of light-years. The mathematics of signal decay creates a severe practical limitation on the distances at which civilizations at similar technological levels could reliably communicate with one another or transmit any detectable signal. The implications are staggering. Humanity's most powerful radio transmitters beam signals that fade into silence just beyond our own planetary neighborhood. The radio broadcasts that have been leaking from Earth into space for the past century, the early radio and television transmissions that have escaped our atmosphere, these signals are now scattered across light-years of space, growing fainter with each passing moment, becoming indistinguishable from background radiation from the cosmos. Any civilization at Alpha Centauri, our nearest stellar neighbor, would be unable to detect our most powerful broadcasts. They would hear only silence, only the natural hum of cosmic radiation and stellar noise. This harsh reality suggests that the search for intentional alien broadcasts might be fundamentally misguided. Perhaps we should not be listening for signals that traveled across light-years of space, because the mathematics of radio propagation suggest that such signals would be undetectable at interstellar distances unless the broadcasting civilization possessed technology far beyond our own, technology capable of harnessing the power of entire stars. The light year itself is not just a measurement of distance, but a fundamental barrier to contact between civilizations. Light is the fastest thing in the universe, and nothing with mass can ever reach its speed, much less exceed it. This means that even the nearest star systems represent communication delays that fundamentally alter what connection between civilizations could look like. A message sent from Alpha Centauri would take 4.3 years to reach Earth, and any reply would take another 4.3 years to return, creating a round-trip communication delay of nearly a decade. At greater distances, this delay becomes catastrophic for any meaningful dialogue. A civilization 20 light-years away would experience a 40-year round-trip communication delay. By the time a message reached its destination and a response made the journey back, circumstances on both sides could have changed entirely. Governments might have fallen, wars might have started or ended, technologies might have advanced beyond recognition, species compositions might have shifted. The entire context of the conversation would have transformed. This means that real-time dialogue across interstellar distances is fundamentally impossible. Any communication becomes more of a time capsule than a conversation. A civilization at one star would be essentially sending messages into a future they could not predict, hoping that whoever receives them still cares about a conversation that began before their grandchildren were born. More fundamentally still, light-year distances are not merely communication delays. They represent the hard speed limit of the universe itself. Nothing can ever be faster than light in a vacuum. No civilization, no matter how advanced, can circumvent this physical law. Einstein's theory of relativity forbids it absolutely. This is not a limitation of current technology that might be overcome by future innovation. It is a feature of the universe itself, built into the fabric of existence. The speed of light is not a barrier we can break through with enough ingenuity or energy. It is the speed limit of reality itself. Every physicist, every engineer, every visionary who has ever thought about reaching for the stars must confront this immutable truth. We cannot escape it, cannot avoid it, cannot wish it away with sufficiently advanced technology. The universe has embedded this limit in its very structure, and no manipulation of matter or energy can override it. This creates a kind of cosmic isolation that is baked into the very structure of space-time, an isolation that makes the nearest stars feel almost impossibly distant. The light year becomes more than just a distance measurement. It becomes a prison, separating all civilizations from one another by periods of time that dwarf the histories of species and the lifespans of individuals. It is as if the universe itself conspired to keep civilizations apart, ensuring that whatever intelligence might develop elsewhere must remain fundamentally isolated, unable to achieve the real-time interaction that might characterize a galactic community of minds. The nearest habitable worlds we have discovered represent the closest possibilities for finding alien life. Yet even these closest candidates illustrate the staggering distances involved. Proxima Centauri is the nearest potentially habitable exoplanet we know of, located approximately 4.24 light-years from Earth, orbiting within the habitable zone of its star where conditions might theoretically support liquid water. Teegarden's star B, discovered more recently, sits about 12.5 light-years away and is among the most Earth-like exoplanets discovered so far, earning an initial habitability score of 0.97 out of 1.0, nearly perfect. Tau Ceti E, another close candidate, orbits approximately 11.9 light-years away. However, being nearby in astronomical terms remains incomprehensibly distant in human or even civilization-scale terms. A rough estimate suggests there are approximately 2,000 stars within 50 light-years of our solar system, and perhaps 15% of them could potentially host Earth-sized planets within their habitable zones. This would suggest thousands of potentially habitable worlds within a region that sounds almost local when compared to the scale of the galaxy. Yet the vast distances between even these nearby stars make meaningful communication or physical travel between them profoundly challenging and perhaps impossible. Two worlds only 20 light-years apart would be separated by centuries of travel time at anything approaching relativistic speeds. The gap between adjacent, potentially habitable planets in our cosmic neighborhood might be 5, 10, 20, or 40 light-years. These distances stretch across scales that dwarf human history and challenge the very concept of civilization as we understand it. We have discovered that worlds orbiting stars near our own are not clustered densely together. They are scattered through space like rare jewels in an infinite void. The distances between them force us to confront a troubling possibility. Perhaps the habitable planets are distributed sparsely enough that civilizations rarely, if ever, encounter one another, even within the same galaxy. Even if thousands of habitable worlds exist within 100 light-years of Earth, the nearest one might still be far enough away that detecting it or communicating with its inhabitants becomes practically impossible. The neighborhood of stars becomes less like a city and more like a desert, where oases are separated by vast stretches of empty landscape, and travel between them requires crossing distances that strain the capabilities of any civilization, no matter how advanced. The detection range of our current technology, despite being more advanced than ever before in history, captures only a minuscule sphere of cosmic space. The Green Bank telescope, one of the most sensitive radio telescopes ever built, could theoretically detect a radio signal equivalent to Earth's current technological capabilities from a distance of only about 23 light-years. Given the scale of the Milky Way, which stretches approximately 100,000 light-years in diameter, our most sensitive instruments can scan less than 0.05% of our galaxy. Recent SETI efforts have expanded beyond our galaxy, scanning approximately 2,800 other galaxies with lower radio frequencies, but the detection range for these distant galaxies is even more limited. We can only detect extraordinarily powerful signals from beyond our galaxy, which would require civilizations far more advanced than our own. Within our galaxy, most modern SETI searches focus on relatively nearby stars within a few hundred light-years. But even at these distances, we can only detect signals from civilizations at least as advanced as ourselves, and realistically, only from civilizations that are broadcasting intentionally with enormous power. This means our search coverage, despite using the best technology humanity has ever created, resembles a single person with a flashlight searching for other flashlights across an entire continent in total darkness. The volume of space we can effectively monitor for signals is so small compared to the total volume of the galaxy that the odds of stumbling upon an active transmission become vanishingly small. Even if civilizations were common, the odds of one being in our detection range, being active right now, transmitting in a direction we're listening, at a frequency we're monitoring, and doing so with enough power to overcome cosmic noise, becomes statistically improbable. Our technology, for all its sophistication, is fundamentally limited by the light-year scale that separates stellar systems. Think about it this way. We have pointed our most sensitive radio telescopes at millions of stars. We have listened patiently for signals from civilizations that might be out there. We have devoted decades of research and enormous resources to this search. Yet we have found nothing. A single confirmed signal, a single message that could not be explained by natural phenomena, would be the most significant discovery in human history. Instead, there is only silence. Scientists continue to refine their methods, expanding search frequencies, increasing sensitivity, monitoring more stars. And still, nothing. The question becomes not whether our technology is limited, but whether any technology limited to the speed of light could ever succeed in finding civilizations scattered across light years of distance, separated by gulfs so vast that even a brief conversation would span generations. The distance between galaxies introduces yet another layer of cosmic isolation that makes the scale we've been discussing seem almost intimate by comparison. Our Milky Way galaxy spans roughly 100,000 light-years from edge to edge and contains an estimated 200 to 400 billion stars. The nearest major galaxy to us, Andromeda, sits approximately 2.5 million light-years away. Between our galaxy and Andromeda lies a void of 2.5 million light-years of essentially empty space. A message traveling at light speed would take 2.5 million years to bridge this gap. This is longer than the entire span of human evolution. Modern humans have existed for only about 300,000 years, meaning the communication delay across even the closest galactic gap is roughly 10 times longer than our entire species has existed. Beyond Andromeda, galaxies are scattered across the universe at distances measured in millions and billions of light-years. The most distant observable galaxies are so far away that light from them takes 13.8 billion years to reach us, meaning we are seeing them as they were in the universe's infancy. Any hypothetical civilization in those distant galaxies would have evolved, thrived, and possibly gone extinct long before their light reached us. This cosmic distance becomes almost absurd, so incomprehensibly vast that human minds struggle to grasp it. Yet billions of galaxies populate the observable universe, each containing billions of stars, most of which probably host planetary systems. The sheer number of potential homes for life is almost unfathomable, and yet they are separated by gulfs so vast that civilization in one galaxy would be almost completely isolated from civilizations in any other galaxy. A work of communicating civilizations could theoretically span our galaxy, but connecting across even to our nearest galactic neighbor seems fundamentally impossible on any realistic timescale. The universe is simultaneously crowded with galaxies and utterly empty. The light we receive from distant galaxies has been traveling for billions of years across expanding space. During that journey, the universe itself has grown larger, stretching the distances even further. When that ancient light finally reaches us, we are seeing not the universe as it is now, but as it was in the distant past. Civilizations in distant galaxies, if they exist, are separated from us, not just by space, but by time. They are not our contemporaries. They are inhabitants of a universe billions of years younger than the one we observe today. Any connection across such cosmic gulfs would be not merely a communication across distance, but a conversation across time itself, with one party speaking to ghosts of civilizations long since vanished. The human perspective on time is shaped by individual lifespans, generational cycles, and historical memory spanning perhaps a few thousand recorded years. When we think about travel, we think in terms of hours, days, or at most years. Yet interstellar travel operates on entirely different timescales that strain our intuitive understanding. If a generation ship were to be sent toward Alpha Centauri, taking 76,000 years to arrive, roughly 3,000 human generations would live and die during the voyage. The civilization that launched the mission would be unrecognizable by the time the ship arrived, if that civilization still existed at all. Languages would have changed beyond mutual intelligibility. Technologies would have advanced dramatically. The political systems, cultural traditions, and then, the genetic composition of humanity might be radically different. The original mission's purpose might have been forgotten entirely. Science fiction often depicts generation ships maintaining connection with a home world, but in reality, the communication delays make this impossible. A ship 10,000 light-years along its journey toward a distant star would be unable to receive meaningful guidance from Earth. Radio signals would arrive vastly delayed, carrying information about events the ship's inhabitants would find historically relevant. By the time instructions from Earth reached the ship, the circumstances that prompted those instructions would have changed countless times. A civilization at the destination would have no context for why this ancient vessel arrived carrying occupants descended from an ancient Earth civilization. The very concept of a coordinated interstellar expedition becomes questionable when the timescales involved exceed the durability of any known civilization. Even our oldest human civilizations have existed for only 5,000 to 10,000 years. Asking a civilization to maintain a project spanning 76,000 years tests the limits of what any society could realistically achieve. Time itself becomes a barrier to connection, as fundamental as distance. Distance and time conspire together to isolate civilizations. A journey to the nearest star takes longer than human civilization has existed. By the time explorers arrived, they would find themselves in contact with a civilization that had evolved for thousands of generations while they were gone. They would be like ancient explorers from a vanished age, stepping into a future they could never have anticipated. The assumption that civilizations persist long enough to maintain contact across interstellar distances becomes questionable. History shows that civilizations rise, flourish, and fall. Empires collapse. Technologies are lost and rediscovered. Languages become unrecognizable. The question is not merely whether, 1, we can send a message across light years of space, but whether the civilization that receives it will care about a message from ancestors who lived so long ago that their world has become mythology. The Great Silence is perhaps the most striking observation about our search for alien civilizations. Scientists have applied increasingly sophisticated instruments and methods to scan the sky for evidence of extraterrestrial intelligence. Radio telescopes have been listening since the 1960s, monitoring millions of frequencies across thousands of stars. Modern surveys encompass millions of stars, yet not a single confirmed signal has emerged from the cosmos. There is no reliable evidence that aliens have visited Earth. We have observed no intelligent extraterrestrial life with current technology, and SETI has found no definitive transmissions from other civilizations. The universe, apart from Earth, appears dead. This silence stands in stark contradiction to what the mathematics suggests all to be true. Given 200 to 400 billion stars in the Milky Way, many of them resembling our Sun, and a significant fraction probably hosting Earth-like planets in habitable zones, simple probability suggests that intelligent civilizations should number in the thousands or even millions. The Milky Way is approximately 10 billion years old, which is more than twice the age of Earth. This means civilizations could have arisen billions of years before life even emerged on our planet. A civilization with even modest technological advancements spreading across the galaxy at slow speeds could theoretically colonize the entire Milky Way thousands of times over in the time that has elapsed. Yet we see no signs of this expansion. No visitors, no radio broadcasts, no massive engineering projects. Fizzy broadcast. Sist Enrico Fermi famously asked in 1950, "If aliens exist, where are they?" This question has haunted astronomy and astrobiology for over 7 decades because the mathematical expectation of abundant alien civilizations collides with the observational reality of cosmic silence. The paradox doesn't have an obvious resolution. Either our assumptions about the prevalence of life are drastically wrong, or something prevents civilizations from spreading, communicating, or existing long enough to be detected. Distance might be a substantial part of the answer. The silence we observe could reflect not an absence of life, but the practical impossibility of bridging the vast gulfs between worlds. Perhaps the universe is teeming with civilizations, each trapped in its own stellar neighborhood, unable to break free from the isolation imposed by light years and the physics of the universe itself. Each civilization might conduct its own searches, listening to its own sky, finding nothing, concluding that they are alone. The cosmic silence could be the silence of a universe where communication is theoretically possible, but practically impossible, where every world is separated from every other by distances so vast that connection becomes a statistical impossibility. The most straightforward explanation for the great silence might also be the most profound. Perhaps civilizations are separated by distances so vast that they cannot find one another regardless of how common they actually are. The Milky Way spans 100,000 light-years, but habitable zones suitable for life as we understand it are not randomly distributed throughout this volume. They cluster around the right types of stars, maintaining distances from other favorable locations. Even if 1% of stars host habitable planets, and 1% of those have developed technological civilizations, the resulting civilizations might still be separated by hundreds or even thousands of light-years. 2 civilizations separated by 1,000 light-years could not establish meaningful contact. A radio signal would take 1,000 years to bridge the gap, arriving to a civilization that is not the same one that sent the original message. A generation ship would require millions of years of travel to make the journey, assuming it could overcome the engineering challenges of such an undertaking. A civilization might search for others for decades or centuries and find nothing simply because the nearest civilization is 500 light-years away beyond their detection horizon. In statistical terms, if civilizations are scattered through the galaxy with an average separation of even just 100 light-years, and each civilization remains active and detectable for only a few thousand years, the probability of 2 civilizations being both active and detectable at the same time, while being close enough to communicate, becomes extraordinarily small. Distance acts as a filter that isolates civilizations from one another, turning a statistically possible galaxy full of life into a practically empty cosmos where each civilization dwells in isolation. The sheer silence of space might reflect not the absence of life, but its profound and inevitable separation. This possibility is perhaps more lonely and more profound than the idea that we are alone. It suggests that the universe might be full of intelligent minds, each capable of wonder, philosophy, science, and art, each looking up at their sky and searching for others, each finding only silence. The isolation imposed by distance becomes a cosmic tragedy. Every civilization is surrounded by billions of stars, yet separated from neighboring civilizations by gulfs too vast to cross. Every world is a kind of island, isolated not by water but by light years, cut off from the larger community of conscious beings that might exist in the galaxy. This is the cruelty of a universe where life can arise in countless places, but cannot reach those places from anywhere else. Understanding probability in the context of cosmic searches requires accepting that mathematical possibility is not the same as practical likelihood. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of intelligent extraterrestrial civilizations in the Milky Way by multiplying 7 factors together: the rate of star formation, the fraction of stars with planets, the average number of planets in habitable zones, the fraction of habitable planets that develop life, the fraction of life-bearing planets that develop intelligent life, the fraction of intelligent civilizations that broadcast detectable signals, and the average lifetime of such civilizations. Although scientists can estimate some factors with reasonable confidence, others remain almost entirely uncertain. We know the Milky Way contains 200 to 400 billion stars. We can observe that many stars have planetary systems, and we can estimate habitable zone frequencies. However, the fraction of habitable planets that actually develop life remains utterly unknown. We have precisely one example: Earth. We cannot determine if life arises on 1% of habitable planets, or 0.001%, or 10%. The fraction of life-bearing worlds that develop intelligent civilizations is similarly mysterious. The intelligent life on Earth represents a single data point after 4 billion years of biological evolution. We cannot know if intelligence is an inevitable outcome of life or an extraordinarily rare accident that happens perhaps once per galaxy. The lifetime of technological civilizations is also speculative. Will humanity survive for 1,000 more years, or 1 million? Do civilizations typically destroy themselves, or transcend their limitations? The Drake equation becomes less a prediction and more an organization of human ignorance. When scientists plug in optimistic values, they get millions of civilizations. When they plug in pessimistic values, they get perhaps 1 or 2 in the observable universe. The same mathematical framework produces radically different results, depending on assumptions about factors we cannot directly observe. This profound uncertainty means that observable evidence becomes supremely important. The fact that we detect nothing, despite our searches, suggests that either life is far rarer than optimistic estimates suggest, or the factors limiting contact are far more severe than we typically assume. Distance could be the primary factor determining this outcome. The universe might contain countless intelligent civilizations, and yet they might all be invisible to one another, trapped behind horizons of light years that make detection and contact impossible. The Drake equation might give us millions of civilizations, but the equation does not account for the practical problems of distance. It is an equation that addresses existence, but not accessibility. A civilization might exist and still be utterly undetectable, forever beyond our reach, separated from us not by physics that might one day be overcome, but by the fundamental laws of the cosmos itself. This is perhaps the most troubling answer to Fermi's question. They are out there, but they are too far away, and they will always be too far away. When we consider the Drake equation and the distances it implicitly reveals, we begin to see how thoroughly space has isolated the possible civilizations scattered throughout the galaxy. The Drake equation, developed by astronomer Frank Drake in 1961, represents an attempt to estimate the number of intelligent extraterrestrial civilizations in the Milky Way. It multiplies together 7 factors: the rate of star formation, the fraction of stars that host planets, the fraction of those planets in habitable zones, the fraction where life actually develops, the fraction that becomes intelligent, the fraction that broadcasts detectable signals, and the average lifetime of those civilizations. The equation appears mathematical and precise, yet it is fundamentally an equation of ignorance. We estimate some factors with reasonable confidence. We know the Milky Way contains roughly 200 to 400 billion stars. We know that planetary systems are common, that we have discovered thousands of exoplanets, and that many orbit in regions where liquid water could theoretically exist. But other factors in the equation remain almost entirely mysterious. We cannot know what fraction of habitable planets actually develop life. We have one example, Earth. We cannot determine whether life arises on 1% of habitable worlds, or 1 in a billion. The fraction of life-bearing planets that develop intelligent civilizations is equally obscure. How often does intelligence emerge? Is it an inevitable consequence of life, or an extraordinarily rare accident that happens perhaps once per galaxy? The lifetime of technological civilizations remains speculative. Will humanity survive 1,000 more years or 100,000? Do civilizations typically destroy themselves or transcend their limitations? When scientists input optimistic values into the Drake equation, they obtain millions of potential civilizations. When they use conservative estimates, the result is perhaps 1 or 2 in the observable universe. The same mathematical framework produces radically different conclusions depending on assumptions about factors we cannot directly observe. The uncertainty is so profound that the Drake equation might as well be a study of how many different answers scientists can obtain by changing their assumptions. It demonstrates the limits of trying to predict the abundance of alien civilizations when so many variables remain unknowable. The equation itself becomes a meditation on ignorance rather than a path to knowledge. What becomes clear is that distance, while not explicitly part of the Drake equation, dramatically constrains what the equation actually means in terms of real-world consequences. The equation tells us how many civilizations might exist, but it says nothing about whether those civilizations can find one another, communicate, or establish lasting contact. A universe containing millions of civilizations separated by thousands of light years is functionally a universe where contact is impossible, according to the laws of physics as we understand them. The Drake equation optimistically estimates that we should not be alone, yet that same universe might ensure that any other civilizations remain utterly isolated from us, forever beyond our reach, and forever separated by gulfs that no technology could bridge. The mathematics of probability becomes almost meaningless when applied to a cosmos of such staggering scale, so vast that statistical certainty becomes statistical impossibility. Civilizations developing in different cosmic eras presents another fundamental problem that distance exacerbates catastrophically. The Milky Way is approximately 10 billion years old. This time span is staggering, more than twice the age of Earth itself. Yet civilizations do not develop simultaneously across the galaxy. A civilization might have emerged around a star billions of years before Earth even formed, developing technology while the universe was still young. Another might develop billions of years in the future, long after humanity has vanished from the cosmos entirely. The probability that two civilizations would reach technological maturity at overlapping moments in time becomes vanishingly small when you consider the vast span of cosmic history available. The window of overlap becomes smaller and smaller the farther apart civilizations develop in time. Imagine a civilization that achieved spacefaring capabilities 5 billion years ago, near the dawn of the galaxy's formation. Where are they now? They could have colonized the entire Milky Way thousands of times over. In the intervening epochs, they could have built structures visible across entire light years. They could have left unmistakable evidence of their presence throughout the galaxy, yet we see nothing from them. Either they destroyed themselves, a possibility the Great Filter theory suggests is likely, or they vanished due to some catastrophe we cannot fathom, some disaster that transformed the galaxy or prevented them from continuing their work. Or they left the galaxy entirely, escaping to other cosmic structures beyond our observation and understanding. They might have transcended their physical forms entirely, becoming something so different from biological life that we would not recognize them as civilization at all, leaving behind only silence and mystery. Or perhaps they simply chose not to interact with the galaxy at large, settling into quiet isolation. Alternatively, civilizations might be constantly arising and falling, with each one lasting only thousands or millions of years before collapsing into silence. The rise and fall of civilizations might be like the breathing of the galaxy itself. A civilization emerging 100,000 years ago might have broadcast signals for 10,000 years before internal conflict or environmental catastrophe ended their technological age. By the time we began listening with our radio telescopes a few decades ago, their signals had been silent for 90,000 years. We would never hear them. We would only encounter the silence left behind, not even knowing we were surrounded by echoes of dead civilizations that had once gazed at the stars and wondered if anyone was listening. The timeline problem compounds the distance problem in ways that defy simple calculation. Even if civilizations are common, even if the Drake equation suggests millions should exist, they are scattered, not just across space, but across time. The probability that another civilization is currently active, currently broadcasting, currently visible at this exact moment in cosmic history, and close enough for us to detect them through the fog of distance and noise, becomes almost infinitesimally small. The odds are like trying to find a specific grain of sand on all the world's beaches, while also requiring that the grain be lit by a specific color of light at a specific moment. We are searching for a specific civilization at a specific moment, across billions of stars and billions of years, using instruments sensitive to an incomprehensibly narrow band of cosmic signals. The universe could be a graveyard of dead civilizations, each one having risen and fallen before any other civilization in its region developed to the point where they could search the sky. The loneliness is not that there are no civilizations. The loneliness is that they are separated by so much time that they never meet. The Great Filter hypothesis offers one explanation for why, despite the mathematical suggestion that civilizations should be common, we find nothing but silence. Economist Robin Hanson proposed this theory in 1996. The Great Filter, he suggested, represents a transition so difficult that virtually no species can make it without perishing in the attempt. Perhaps it is the transition from simple chemistry to life itself, a step so improbable that it rarely occurs. Perhaps it is the transition from single-celled organisms to complex multicellular life, requiring cooperation on a scale most organisms never achieve. Perhaps it is the development of intelligence itself, consciousness emerging so infrequently that it represents the rarest gift in the universe. Or perhaps, and this is the most true, hubling possibility, it is the transition from technological civilization to a form that can escape self-destruction. Any species capable of harnessing sufficient energy to leave its home planet must master technologies that can also be weaponized, that can cause planetary scale destruction, that can lead to wars between increasingly powerful factions. These are the same technologies that could spell civilization's doom. This is the Great Filter, the barrier that separates the living from the dead. If this barrier is located before we reach it, humanity might be extraordinarily rare, perhaps unique in our region of the galaxy. If the Great Filter lies ahead of us, it means civilizations that reach our level of development almost always destroy themselves before they can spread beyond their home worlds. This would explain the silence. The galaxy could be full of civilizations, most of them destroyed before they reach the stage of interstellar expansion. Each species rises, develops the knowledge and capability for planetary destruction, then faces a moment of choice, a critical juncture, where they either transcend their destructive impulses or succumb to them. Some survive that moment of testing. Most do not. The question that haunts our species is whether we are one of the survivors or one of the species destined to self-destruct, to rise brilliantly only to fall in nuclear fire or environmental collapse. The great filter transforms distance from a problem of physics into a problem of biology and behavior. Even if two civilizations existed at the same time and in nearby star systems, close enough that contact should theoretically be possible, they would never meet because one or both would have already self-destructed. Distance becomes irrelevant when civilizations eliminate themselves through warfare, environmental collapse, or some other catastrophe. The Great Filter suggests that our search for alien signals might be fundamentally doomed, not because space is too vast, but because very few civilizations ever survive long enough to broadcast their presence to anyone. The silence we hear reflects not the vastness of space, but the fragility of civilizations that rise briefly and then vanish into the cosmic night. Communication windows and timing introduce another temporal dimension to the distance problem that makes contact even more unlikely. Imagine that somehow, against overwhelming odds, two civilizations existed simultaneously and were close enough that radio signals could bridge the gap between them. This alone is so improbable that we should pause and consider how rare this scenario actually is. Even then, even if this miracle occurred, communication would face constraints that seem almost designed to prevent connection. A civilization would need to broadcast at exactly the right frequency, at exactly the right time, in exactly the direction where another civilization happened to be listening. The precision required is staggering. Our own radio broadcasts have been escaping Earth for roughly a century. These early transmissions expanded outward in a sphere growing at the speed of light, expanding through space like ripples on an infinite pond. Some of them have traveled light years from Earth, spreading across vast distances, but their power has diminished according to the inverse square law. A receiver positioned 23 light years away might barely detect our most powerful broadcasts, assuming it was pointed in the right direction and tuned to the right frequencies among millions of possible frequencies. Any civilization less technologically advanced than we are would not detect us at all, would hear only background cosmic noise. Any civilization at our level would barely detect us, if at all, beyond a handful of light years. The problem is that we are not broadcasting with intention. We are leaking signals accidentally, but the timing problem is equally severe. Earth's technological civilization has existed for perhaps 150 years, a blink in cosmic terms. Our radio broadcasting has been continuous for roughly a century. If a civilization 100 light years away had started listening 150 years ago, they still would not have received any of our transmissions today, because the radio waves carrying our earliest signals have only traveled 150 light years through space. A civilization 200 light years away would never hear from us unless we continue broadcasting for another 100 years, unless we persist with radio technology for a century more. If we stopped broadcasting tomorrow, if we abandoned radio in favor of new technologies, any civilization beyond our current detection horizon would never know we existed. We would vanish as if we had never been. Leaving no trace for distant ears to ever find. The radio era of Earth might be a brief flicker in cosmic history, lasting only a few centuries before we move to different technologies or before we destroy ourselves. Our window of transmission overlap with distant civilizations is narrow, random, and likely non-existent. It is a lottery with odds that make winning the jackpot look certain. It is as if two ships passing in the night, each carrying a radio would need to be transmitting on compatible frequencies, within visual range, at the exact same moment, and able to recognize each other's signals as intelligent communication rather than background noise. The probability of this occurring by chance across billions of stars is almost zero. The universe seems structured to prevent contact through a combination of space and time that makes meaningful connection between civilizations almost statistically impossible. The passing of civilizations in cosmic time creates a rhythm where contact windows open and close like breathing, and two civilizations almost never happen to be awake at the same moment. When one civilization is broadcasting, another may be silent, dormant, or entirely extinct. When another civilization finally awakens and begins to listen, the first may have long ago fallen quiet, its message lost in the past. The expansion of the universe introduces a factor that distance alone does not capture. The universe is not merely vast, it is expanding, and that expansion means the distances between galaxies are growing continuously. Space itself is stretching, pushing distant structures farther apart with each passing moment. This is not a metaphor or a simplification. The fabric of space-time is actually growing, increasing the distance between all objects not bound together by gravity. Within our own galaxy, this effect is less pronounced because gravity binds our stellar neighborhood together. But on larger scales, expansion becomes the dominant force. A galaxy 10 billion light-years away is not just far away, it is receding from us at speeds approaching the speed of light itself, driven by the expansion of space. This means that for galaxies beyond a certain distance, their light will never reach us, no matter how long we wait. The expanding universe creates a cosmic horizon, a boundary beyond which we cannot see, cannot detect, cannot know. More troubling still, the expansion of the universe means that distances are not static. The gap between our galaxy and another galaxy that was 5 billion light-years away a billion years ago is now larger. The universe is spreading everything apart with relentless force. For civilizations attempting to communicate, this expanding universe presents a problem that gets worse over time. A signal traveling across the expanding universe does not simply grow fainter. It must also traverse space that is being created between the transmitter and receiver as the universe stretches. For distances greater than roughly 5 gigaparsecs, or 16 billion light-years, the expansion of the universe actually prevents signals from ever reaching us, no matter when they are sent, because space is expanding faster than light can travel through it. The universe has embedded an absolute ceiling on how far signals can travel across cosmic distances. Within our galaxy, this effect is negligible, but it illustrates a principle that should terrify any civilization seeking others. The universe actively works against contact. It expands, it stretches, it creates more distance between all structures over time. Two civilizations that manage to develop simultaneously in nearby star systems would find that the universe, simply by existing and expanding as the laws of physics dictate, continually increases the distance between them. Over millions of years, the relativistic motions of stars through the galaxy would also increase distances, moving civilizations farther apart in space. Stars are not stationary. They orbit the galactic center. They drift with the arms of the galaxy. They move through space in patterns that gradually separate them from one another. The universe does not merely present vast distances as an obstacle. It continuously increases those distances, making contact harder with each passing epoch. A civilization that began broadcasting a message today, hoping it would reach a distant civilization, would be sending that message into a universe that was perpetually expanding, perpetually stretching, perpetually making the destination more distant. By the time the signal arrived, if it ever did, it would arrive to a world that was even farther away than when the message was sent. The receiver would be older, farther, and possibly no longer interested in a message from the distant past. The energy requirements for interstellar signals represent a barrier that makes the vast majority of civilizations fundamentally unable to communicate across the vast distances they face. To broadcast a signal strong enough to be detected across light years of space requires energy on scales that challenge our intuition. The Kardashev Scale, developed by astrophysicist Nikolai Kardashev, provides a framework for understanding this problem. Humanity currently uses approximately 17 trillion joules per second, placing us at roughly 0.72 on the Kardashev scale. To reach Type 1 civilization status, capable of harnessing the total energy output of a planet, humanity would need to increase our energy consumption by roughly 1 million times. Imagine increasing your energy use by a factor of 1 million. That would be like jumping from individual houses powered by fire to an entire civilization harnessing hurricanes, earthquakes, and the heat of the entire planetary interior. Each step on the Kardashev scale represents an increase in available power by a factor of roughly 10 billion. To broadcast a signal that could be detected reliably across interstellar distances, a civilization would need to use extraordinary amounts of power. A Type 1 civilization, harnessing planetary scale energy, could broadcast detectable signals across star systems. A Type 2 civilization, capable of harnessing the output of an entire star, could broadcast across the galaxy. But any civilization below Type 1 status would essentially be silent to the cosmos, their signals too weak to penetrate the cosmic noise at distances greater than a few light years. This creates a cruel paradox. Humanity is just beginning to develop the technologies that might allow space travel. Yet we are far from the energy capabilities required to broadcast signals reliably across interstellar distances. We are perhaps 100,000 years away from being able to speak to the stars with sufficient power to be heard. We hear radio signals from Earth's atmosphere leaking into space. Yet these signals fade to silence within a few light years. Any civilization at our current technological level or below it would be completely unable to send signals that could be detected at star-spanning distances. Only civilizations that have advanced far beyond our own level would have any realistic chance of broadcasting across the cosmos. This means that the search for alien signals, as SETI currently conducts it, is inadvertently searching only for civilizations so advanced that they dwarf our own technological achievement. We cannot hear other civilizations at our level. We cannot detect their accidental radio leakage. We can only detect deliberate, high-powered broadcasts from civilizations far more advanced than we are. The likelihood of finding such broadcasts and the likelihood that such broadcasts are being made at all becomes vanishingly small when you consider that most civilizations would be at various early stages of development, unable to project signals across the vast spaces between stars. The search has inadvertently set a bar so high that only godlike civilizations could clear it. The zone of habitability around stars further complicates the distance problem by concentrating the possible locations where civilizations might emerge. The habitable zone is the region around a star where temperatures allow liquid water to exist on a planetary surface. For a star like our Sun, this zone extends roughly between 0.95 and 1.37 astronomical units from the star. For cooler stars, the habitable zone is closer. For hotter stars, it is further. This zone is not infinitely large. It is a specific ring of distance where conditions are just right. The problem is that habitable zones around different stars are located at different distances from their stars. A planet in the habitable zone of Alpha Centauri A exists in a different location relative to its parent star then a planet in the habitable zone of Alpha Centauri A exists in a different location relative to its parent star, then a planet in the habitable zone of Alpha Centauri A exists in a different location relative to its parent star, then a planet in the habitable zone of our Sun. When you consider all the possible stars in the galaxy with all their different habitable zones, you realize that habitable planets are distributed throughout space in a pattern that is neither uniform nor predictable. They are scattered across the galaxy like islands in an ocean, isolated by water that never ends. A civilization developing on a world in one habitable zone might be separated from the nearest habitable world by dozens of light years, or by hundreds, or by thousands. The habitable zone around each star concentrates life, but it does not cluster civilizations together into communities. The gap between the habitable zone of one star and the habitable zone of the next might easily span light years, creating barriers of uninhabitable space that must make travel between worlds nearly impossible. This dispersion means that civilizations are isolated by distance, not just because space is vast, but because the places where civilizations can develop are scattered widely throughout that vast space. Even a relatively advanced civilization could search nearby star systems and find them empty, devoid of habitable zones, despite the galaxy containing billions of potential habitable worlds in total. The search might be endless, yielding nothing but dead rocks. The distance between habitable zones becomes another factor that makes neighboring civilizations improbable and meeting other civilizations nearly impossible. Each island of habitability sits in splendid isolation, surrounded by the void. The lifespans of technological civilizations present a temporal problem that distance amplifies relentlessly. A civilization might exist for thousands of years, or for millions, or it might collapse within decades. We do not know. History suggests that human civilizations have fallen apart within centuries or millennia. Yet we do not know whether this is typical or unique for technological species. If civilizations typically survive only for thousands of years, the window during which any two civilizations could theoretically communicate becomes extraordinarily narrow. Imagine a civilization that develops spacefaring technology and begins broadcasting signals. If that civilization lasts 10,000 years before succumbing to some catastrophe, then another civilization within detectable range, old need to reach technological maturity, develop radio astronomy, and begin listening all within that same 10,000-year window. If the second civilization develops 5,000 years after the first, it would have only 5,000 years to detect the first civilization's signals before they ceased. If the second civilization develops after the first has already fallen silent, they would find only empty space and never know that another conscious species had existed nearby, had gazed at the same stars, had asked the same questions about whether anyone was listening. Most likely, civilizations would not overlap in this narrow window at all. A civilization might broadcast for 10,000 years, then vanish. A millennium later, another civilization might arise in the same region, but the first civilization would be long silent, and they would never know they had predecessors. The timeline of civilizations creates a problem as severe as the distance problem, and the two together become multiplicative. Even if civilizations are relatively common, their brief existences in cosmic terms ensure that contact windows are vanishingly small. A civilization lasting 1,000,000 years is a type of immortality in cosmic terms, yet 1,000,000 years is still a mere blink in a galaxy that has existed for 10 billion years. The probability that two civilizations would develop, reach technological maturity, and maintain active contact within overlapping lifespans becomes astronomically small. when you factor in the distance separating them, the time it takes for signals to travel, and the brief existence of any individual civilization. It is as if civilizations are fireflies, blinking on and off, and two fireflies almost never blink at the same moment, in the same place. Observable signatures across distance become increasingly difficult to detect. As the distance increases, compounding every other limitation we have discussed. Planets produce spectroscopic signatures that we can analyze. Chemical compositions revealed when their parent star's light filters through their atmospheres. A sufficiently advanced civilization using spectroscopy might be able to detect technological gases in a planet's atmosphere, chemical signatures that could not arise naturally but must be products of industrial activity. Yet detecting such signatures requires the planet to pass between us and its star, requires us to be observing at the right moment, requires the signatures to be present in sufficient concentrations to overcome background noise and cosmic interference. Even planets orbiting nearby stars are dim when observed this way. A technological civilization orbiting a planet around Alpha Centauri would be almost impossible to detect using our current spectroscopic techniques, despite Alpha Centauri being our nearest star system. The signal is so weak that it drowns in the cosmic noise. Megastructures like Dyson spheres, vast artificial constructs surrounding stars to capture waste heat and radiation, would produce infrared signatures potentially detectable across space. Yet as distance increases, these infrared emissions become fainter. An infrared telescope scanning for Dyson spheres must contend with natural infrared sources, dust clouds, and radiation from countless stellar objects. The signal from an artificial structure becomes harder to distinguish from background noise with each doubling of distance. Scientists have scanned hundreds of nearby stars for potential Dyson sphere signatures and found nothing but ambiguous candidates that probably represent natural phenomena. The search space is enormous, and the signals we are looking for are extraordinarily faint. Finding a technological signature becomes like looking for a single lit candle in a vast landscape filled with millions of other lights, both real and illusory. Direct observation of alien worlds and civilizations across light years of distance remains beyond our technological capabilities and will likely remain so for the foreseeable future. We cannot see other civilizations even if they exist, and this invisibility goes both ways. Other civilizations cannot see us, cannot observe our cities and lights and signs of technology, cannot detect us unless we broadcast deliberately and powerfully into space. We are invisible to each other, shrouded in the darkness of distance. The challenge of synchronous development ties together many of the problems we have discussed. For two civilizations to meaningfully contact one another, several impossible coincidences would need to occur simultaneously. Both civilizations would need to reach technological maturity. Both would need to develop the same technologies for detecting or transmitting signals, or at least compatible enough technologies to allow communication. Both would need to be active and broadcasting or listening within a window of time that overlaps. Both would need to have the energy resources to maintain communication across vast distances. Both would need to be separated by a distance small enough that signals could cross it within a reasonable time frame. Both would need to be searching for signals at frequencies the other was using. Both would need to interpret any signals they received as being from an intelligent source rather than natural phenomena. Each of these conditions individually has a low probability. The probability that all of them align simultaneously becomes almost unimaginably small, approaching zero. A civilization might broadcast for 10,000 years on frequencies that another civilization never thinks to monitor. A second civilization might develop 50,000 years after the first, missing any overlap by millions of years. A third civilization might exist but never develop radio technology, communicating instead through some other means we have never considered, perhaps through methods we lack the framework to even imagine. A fourth might develop radio technology but lack the mathematical knowledge to decode alien messages, interpreting them as noise. A fifth might develop the knowledge but choose not to broadcast, fearing the consequences. The universe becomes a place where contact is not merely difficult but statistically nearly impossible, despite containing billions of potential worlds. The problem is not that civilizations do not exist. The problem is that the requirements for two civilizations to find one another create such a tangled web of coincidences, timing, technology, and capability that the odds become vanishingly small. Distance multiplies these difficulties. Communication windows shrink to nothing. Signals fade into cosmic noise. Civilizations rise and fall without ever knowing that somewhere, perhaps just light years away, another conscious species gazed up at the stars and wondered if anyone was listening. The universe might be full of lonely civilizations, each searching, each finding only silence, each concluding that they are alone. This loneliness might be the truest description of the cosmos that we can offer. It might be more profound than any description of vastness or time. The Milky Way itself contains zones of habitability that vary dramatically depending on distance from the galactic center. Not all regions of our galaxy are equally hospitable to life or to the emergence of technological civilizations. The galactic core is flooded with intense radiation from countless stellar objects in close proximity and populated by stars in such close proximity that they would destabilize any planetary orbits around them. Gravitational chaos would rip worlds apart before they could develop stable climates for billions of years. The outer reaches of the galaxy, meanwhile, contain fewer stars and less elemental enrichment from stellar explosions, making complex chemistry and planetary formation less likely to occur. When the universe formed approximately 13.8 billion years ago, the first stars contained only hydrogen and helium, the simplest elements. Heavier elements that make planets and life possible, elements like carbon and oxygen and iron, are created only within stars, through nuclear fusion, and released explosively when those stars explode, as supernovae. The older regions of the galaxy have had more time for this enrichment process to accumulate, while younger regions remain relatively primitive in their composition, lacking the heavy elements necessary for planet formation. Between these extremes lies the galactic habitable zone, a region where conditions balance to permit the emergence of life on planetary surfaces. This zone contains sufficient stellar density for planetary systems to form, and sufficient elemental abundance for rocky worlds to exist, yet avoids the chaotic gravitational environment of the galactic core, where stars are too close to permit stable planets. This habitable zone is itself enormous, spanning tens of thousands of light years in width and depth, yet it represents only a fraction of the galaxy's full extent. Within this habitable zone, civilizations could theoretically exist, yet they remain distributed across such vast spaces that even being in the same galactic neighborhood provides no guarantee of proximity to other civilizations. A civilization on one side of the habitable zone and another on the opposite side could be separated by thousands of light years, even though both exist in regions favorable to life. The geometry of the galaxy means that regions supporting intelligent life are not clustered together like villages or cities on a landscape, but dispersed throughout a vast volume of space, sometimes separated by hundreds of or thousands of light years. The habitable zone itself becomes another layer of the distance problem. Civilizations are not randomly scattered throughout all of space, but concentrated in zones where conditions permit their emergence. Yet even this concentration still results in separation across light years, sometimes across tens of thousands of light years. The very forces that make certain regions habitable also spread civilizations across distances too vast for meaningful connection. A civilization in the Sagittarius Arm might be thousands of light years away from another civilization in the Orion Arm, both occupying habitable zones, yet utterly isolated from each other by the gulf between galactic arms. They could both exist simultaneously, both conscious and wondering, yet forever separated by distances that make any meaningful contact impossible. The habitable zone concentrates life, but only at tremendous separation. Communication lag becomes almost absurd when you consider the practical implications of interstellar contact over anything but the closest distances. Imagine a civilization on a world orbiting Proxima Centauri, our nearest star system at 4.24 light-years away, attempting to send a message to Earth. The signal travels at light speed, moving through the vacuum of space with no faster option available according to the laws of physics. It takes just over 4 years to arrive at Earth. A reply would take another 4 years to return to Proxima Centauri. A single exchange of information spans 8 years. By the time a response reaches the original sender, the context of the conversation might have shifted entirely. A government that existed when the message was sent might no longer be in power, replaced by revolution, or election, or succession. Scientific theories considered cutting edge might have been superseded by new discoveries. An economic crisis might have developed and resolved. A war might have ended or begun. The entire political or scientific landscape could have transformed in fundamental ways. This communication lag transforms interstellar contact from dialogue into something more akin to leaving messages in bottles, hoping that generations hence someone will find and respond to your thoughts. Direct conversation becomes impossible. At even greater distances, the lag becomes increasingly catastrophic. A civilization 20 light-years away would experience 40-year delays in receiving responses. Imagine asking a question and waiting 4 decades for an answer. 6 years away, responses take 120 years. At distances of hundreds of light-years, communication becomes stretches of time that exceed the typical lifespans of most institutions, sometimes exceeding centuries or millennia. Governments might fall, replaced entirely by successor entities with different values and priorities. Academic institutions might vanish, their knowledge dispersed or lost. Technologies might become obsolete and irrelevant. The conversation partners might not even recognize each other's transmissions as relevant by the time responses arrive, as if they were reading words written by ancestors. Real-time dialogue becomes impossible. Meaningful negotiation becomes impossible. Building relationships becomes impossible. Establishing treaties or trade agreements becomes impossible. The universe enforces isolation through the simple physics of light's finite speed. This is not a limitation of current technology that future advancement might overcome. This is a fundamental law of nature, embedded in the structure of space-time itself. No civilization, no matter how advanced, can exceed the speed of light according to everything we understand about physics. That speed limit creates a barrier against connection that cannot be circumvented. Any civilization attempting to reach across the stars discovers that the medium they must use to communicate moves too slowly to permit the kind of back-and-forth exchange that characterizes understanding between conscious minds. Dialogue requires rapid feedback, the ability to question, clarify, and correct misunderstandings. The mathematics of distance and light speed create a barrier against meaningful connection that transcends whether signals can be detected. Even if detection were easy, even if signals arrived at full strength, meaningful communication would remain profoundly difficult. The cosmic horizon represents a fundamental limit on the observable universe that impacts any search for distant civilizations and reveals something profound about the structure of reality itself. Beyond a certain distance, the universe is expanding so rapidly that light from distant sources can never reach us, no matter how long we wait or how sensitive our instruments become. This is not a limitation of our technology or something that future civilizations might overcome. This is a property of the universe itself, embedded in the fabric of space-time. The expansion of space is driven by dark energy, a mysterious force that accelerates the growth of cosmic distances with each passing moment. For extremely distant galaxies, this expansion moves them away from us faster than light can travel through space toward us. Their light will never reach Earth. There is a maximum distance from which any light can possibly reach us, a cosmic event horizon beyond which observation becomes absolutely impossible by any means. For observers within our galaxy, this effect is negligible because gravity binds our galaxy together against the cosmic expansion, but it establishes a principle that matters at larger scales. The universe actively prevents observation of distant structures. For galaxies billions of light years away, the cosmic horizon closes completely, becoming unreachable within the age of the universe. Any galaxy beyond a certain distance becomes unobservable, not because it is too faint or too far, but because space is expanding faster than light can traverse it, creating a perpetuous hour recession. This suggests something troubling about reality. The universe does not simply make detection difficult through vast distances and noise. It makes certain regions of space fundamentally unobservable, hidden behind an expanding wall that light itself cannot penetrate. For civilizations attempting to communicate across cosmic distances, this horizon represents an absolute barrier that no technology could overcome. A signal sent from beyond the cosmic horizon toward our galaxy would arrive at speeds slower than the expansion that carries the sender away from us. The message would be perpetually receding, never reaching its destination, forever slipping away into the expanding void. The universe contains built-in barriers to connection that go beyond mere distance. Space itself expands in ways that prevent certain messages from ever arriving. It creates cosmic isolation that is not negotiable, not subject to technological workaround. The silence of the distant cosmos might reflect not an absence of life, but the geometric structure of space and time themselves, which actively prevent distant observers from communicating. The current parameters of SETI searches reveal just how limited our coverage truly is, despite sophisticated technology and decades of effort. The Green Bank Telescope, one of the most sensitive radio telescopes in the world, can detect radio signals from a civilization at Earth's current technological level only if that civilization is broadcasting intentionally from within about 23 light-years. 23 light-years is incomprehensibly small on galactic scales. To put this in perspective, a light-year is the distance light travels in a year, approximately 5.88 trillion miles. 23 light-years is roughly 135 trillion miles. The Milky Way has a diameter of approximately 100,000 light-years. If you imagine the galaxy as a sphere 100,000 miles in diameter, our detection sphere would be less than a mile across. The volume we can search with our most powerful instruments represents only a tiny sphere within our cosmic neighborhood, a negligible fraction of the whole. Within that small sphere exist roughly 2,000 to 3,000 stars. Even if 10% of those stars had habitable planets with intelligent life, we would still be looking at 200 to 300 possible civilizations within our detection range. Of those, How many would be at our technological level or below? How many would be broadcasting on frequencies we monitor? How many would be transmitting strong enough signals to overcome the interstellar medium and reach us? The probability of finding even one civilization by accident becomes extraordinarily small. We are looking for a specific type of signal from a specific type of civilization within a specific narrow frequency range, coming from a specific direction at a specific moment in time. Even if a civilization existed at our technological level and was broadcasting intentionally in our direction, we could only detect them if they happened to be within this small sphere. The probability that any given star within range actually hosts such a civilization is extremely low based on our current knowledge. We have discovered thousands of exoplanets in recent decades, yet finding even one that actually hosts intelligent life remains completely speculative. The search parameters create a situation where we are looking for extremely rare objects within an extremely small volume of space, using equipment that can barely detect them if they exist at all. We are searching for a needle in a haystack made of other haystacks. We are searching blindly through a cosmic darkness. Multiply these limitations across the entire galaxy, and the search becomes functionally impossible. If we imagine expanding our search to other galaxies, the problem becomes even more severe and more demoralizing. The nearest large galaxy beyond our own, Andromeda, lies approximately 2.5 million light-years away. No current telescope could detect radio signals from a civilization at our level within that distance. We would need a civilization millions of years more advanced than us, broadcasting with unimaginable power that we can barely conceive of. The search parameters have inadvertently set a threshold so high that only godlike civilizations could cross it. Most civilizations at various stages of development throughout the galaxy would be completely invisible to our instruments. The search itself may be fundamentally biased toward detecting only the rarest, most advanced civilizations, making it nearly impossible to find typical ones at typical distances. Dyson spheres represent the kind of megastructure that would theoretically be detectable across vast distances because of the enormous amounts of waste heat they would emit into space. Freeman Dyson proposed in 1960 that sufficiently advanced civilizations might construct spherical shells around stars to capture all the star's energy output. Such a structure would be so large that it would encompass the entire orbit of a planet, enclosing the star completely within artificial material designed to absorb radiation and harness energy. A Dyson sphere constructed around our Sun would be at least as large as Earth's orbit, creating a surface area millions of times larger than Earth itself. The heat escaping from the inner surfaces would radiate outward into space, creating infrared signatures that might be visible even from distant star systems if sufficiently sensitive instruments were pointed in the right direction. Scientists have searched for such structures by looking for stars that emit excess infrared radiation in wavelengths that do not match what we would expect from natural stellar emissions. These searches have identified candidates, yet distinguishing genuine technosignatures from natural phenomena becomes extraordinarily difficult at distance. A star surrounded by dust clouds emits infrared radiation that might mimic a Dyson sphere. A star with an extremely cool surface might appear to emit excess infrared when it does not. A binary star system with unusual characteristics might mimic the signature of a Dyson sphere. A young star surrounded by a protoplanetary disk might produce similar infrared signatures to those of an artificial structure. After scanning hundreds of nearby stars, researchers have identified a few dozen candidates that warrant follow-up observation, yet none have proven to be definitive evidence of artificial structures. The sensitivity required to distinguish a genuine Dyson sphere from natural phenomena remains beyond our capabilities at distances greater than a few hundred light-years. Any Dyson sphere more distant than that would appear as only one more infrared source among billions in the cosmic background radiation. The infrared emissions would fade below the level of distinguishable signals, become noise, become invisible. Even a structure so enormous that it would dwarf our entire solar system would become invisible if located far enough away. A Dyson sphere around a distant star would appear to our telescopes as nothing special, just one more point of infrared light among countless others. The megastructure search illustrates that even looking for vast artificial engineering projects does not overcome the fundamental limitation that distance imposes. Size and technology might help detect signals marginally better, but distance ultimately defeats detection efforts. The interstellar medium intervenes between stars and dilutes or distorts signals traveling through it in ways that compound the problems of distance. Space is not a perfect vacuum as we might imagine it. Across the gulfs between stars exist thin clouds of gas and dust, magnetic fields, cosmic rays, and various particles that occupy what we think of as empty space. These materials interact with electromagnetic radiation, absorbing some wavelengths while allowing others to pass, scattering radiation in multiple directions, and changing the properties of signals as they traverse vast distances. Radio signals at some frequencies are absorbed more readily by the interstellar medium than others, particularly lower frequencies. Dust particles scatter light and radio waves, creating extinction that makes distant stars appear dimmer and more reddened. Magnetic fields permeate space and can affect the polarization of radio signals, rotating the plane of oscillation. Plasma clouds can refract signals, bending them slightly from their original paths through what we call dispersion measure effects. These effects accumulate across light-year distances, becoming more severe the farther a signal travels. A radio signal traveling from one star to another must pass through potentially thousands of light-years of material, each layer adding its own distortion. Each interaction slightly degrades the signal, reduces its overall strength, or distorts its character in subtle but significant ways. What begins as a coherent, directed transmission becomes increasingly scrambled and weakened as it propagates. By the time it reaches the receiver, the signal might be so degraded that recognizing it as intelligent communication becomes nearly impossible without sophisticated processing. The receiver would need to possess not only sensitivity, but also advanced algorithms and computational power to decode signals that have been severely distorted by their journey through space. This requirement increases the technological burden on any civilization attempting to detect signals. They must be advanced enough to account for and correct distortions caused by interstellar transmission through the medium. Most civilizations at early stages of technological development would lack the capability to decode such degraded signals, even if they received them with enough strength to notice them. The interstellar medium adds another layer of difficulty to communication, one that works against both the transmitter and the receiver simultaneously. Distance is not merely about the emptiness between stars, but about the material that fills much of that emptiness and actively interferes with the passage of signals. This interference is not something that occurs only rarely or in specific locations. It is a constant feature of interstellar space, present along any path a signal might take between distant stars. It represents a fundamental environmental challenge that any civilization attempting to communicate across light years would need to overcome. The problem becomes even more severe when you consider that different frequencies are affected differently. A transmitting civilization would need to choose frequencies that are least affected by interstellar extinction, yet also frequencies that receiver civilizations might be monitoring for. They would need to encode signals in ways that can survive distortion. They would need to use error correction codes to compensate for degradation. All of this increases the complexity and energy requirement of transmission. Conversely, any receiving civilization would need to know which frequencies to monitor and what error correction schemes to expect. They would need to account for dispersion in their signal processing. They would need computers powerful enough to decode heavily distorted messages. The burden on both sides becomes significant. The interstellar medium thus represents not just a physical obstacle, but an information problem. It degrades and distorts, making every signal harder to recognize as intentional communication. It creates a situation where much of the signal's energy and information is lost simply to environmental noise and interference. The rare Earth hypothesis suggests that the combination of factors necessary for intelligent life to emerge might be so specific and so unlikely that Earth represents something extraordinary rather than typical. While astronomers have discovered thousands of exoplanets in recent years and confirmed that many orbit in regions where liquid water could theoretically exist on their surfaces, the jump from habitable to inhabited to intelligent remains unproven except for one single case: Earth. Our planet possesses numerous features that might be absolutely essential for the development of intelligent life, yet features we cannot easily recognize as common or rare elsewhere. The Earth has an unusual relationship with its moon, which is extraordinarily large relative to the planet itself, and maintains a remarkably stable orbit over billions of years. This moon stabilizes Earth's axial tilt at approximately 23.5 degrees, preventing chaotic climate fluctuations that might make the development of complex life impossible. Without the moon, Earth's axial tilt would wobble unpredictably, causing dramatic swings in climate that would prevent the emergence of complex organisms. The Earth has a strong magnetic field generated by a liquid outer core of molten iron and nickel, protecting the surface from solar radiation and cosmic ray damage. The Earth has plate tectonics, a dynamic planetary surface that recycles elements, brings nutrients from the deep interior to the surface, and creates diverse environments for life. The Earth has an optimal distance from a stable sun-like star, neither too hot to prevent oceans, nor too cold to freeze them solid. The Earth has sufficient metallicity in its composition, containing enough heavy elements to form rocky planets and the building blocks of carbon-based life. All of these features align in a remarkable way, yet we cannot know how rare this alignment is because we have no other examples. Perhaps most habitable planets lack stable moons. Perhaps most worlds have weaker magnetic fields, or lack them entirely. Perhaps most worlds have different levels of plate tectonics or none at all. Perhaps the combination of requirements is so stringent that only 1 in a billion habitable planets develops complex life, and only 1 in a billion complex worlds develops intelligence. If this is true, then intelligent civilizations would be separated by such vast distances that even the entire galaxy becomes virtually empty of other minds. Civilizations would be spread across billions of cubic light years rather than thousands, isolated not by the physics of distance alone, but by the rarity of the conditions that produce them. The rare Earth hypothesis transforms the distance problem from a question of logistics into a question of fundamental scarcity. Even if space were filled with habitable planets, the absence of intelligent life on almost all of them would create the same isolation as if civilizations were rare but clustered together. We would still find ourselves alone. The hypothesis suggests that we might be looking at the problem incorrectly. We tend to assume that because the galaxy is vast and contains billions of stars, intelligent life should be common. But if the requirements for intelligent life are extraordinarily stringent, then the vastness of the galaxy becomes irrelevant. A billion stars might produce only a handful of intelligent civili. civilizations. The universe could be incredibly lonely not because space is vast, but because the emergence of intelligence is an extraordinarily rare phenomenon. Each of us, then, is not only separated by vast distances, but separated by the improbability of ever existing at all. We are unlikely beings in an unlikely universe, finding ourselves alone because the conditions for mind are rarer than we can easily fathom. Resolving the details of alien worlds across interstellar distances remains technically impossible with current and near-future technology, and may remain impossible even with vastly advanced technology. Even if a civilization existed on a habitable world, orbiting a nearby star, we could not see it directly with visual light or any other form of radiation. The most sophisticated space telescopes available today cannot resolve planetary surfaces at distances of even a handful of light years. A planet orbiting Proxima Centauri is so distant and appears so small from Earth that it would be indistinguishable as anything other than a point of light if it were visible at all. We have inferred the existence of exoplanets through indirect methods like measuring the wobble a planet causes in its Saint star as gravity pulls the star back and forth, or observing the slight dimming as a planet passes in front of its star from our perspective. These techniques tell us that a planet exists and allow us to approximate its size and orbit, but they reveal nothing about the planet's surface or any structures on it. We cannot see alien cities, no matter how bright they might be. We cannot observe alien technology or engineering projects. We cannot watch for signs of industrial activity or the presence of intelligent inhabitants. We could not see a Dyson sphere at nearby distances, let alone at galactic scales. The resolution needed to observe another world in detail would require telescopes so enormous that they exceed our current engineering capabilities by orders of magnitude. A telescope capable of resolving the surface details of a planet 10 light years away would need a mirror many kilometers in diameter, larger than any structure humanity has ever built. Such a telescope might not be possible, even in principle, due to the laws of physics and the diffraction limits of light. Any civilization attempting to observe another world for signs of civilization would face the same barrier. They could not see us, no matter how advanced their technology. We could not see them. The distance creates a fundamental invisibility that transcends technology. Signals might travel across the void if pointed in the right direction and tuned to the right frequencies, but observation becomes impossible by direct sight. We search not by looking, but by listening, hoping that some civilization chose to broadcast into space. Yet most likely, civilizations at early stages of development would never think to broadcast into space deliberately. They would remain invisible, their worlds unobserved, their existence unknown to anyone beyond their own star system. Von Neumann probes represent a theoretical solution to the distance problem that actually amplifies the mystery of the Great Silence in powerful ways. Named after mathematician John von Neumann, who theorized about self-replicating machines, these spacecraft could, in principle, allow a civilization to explore and colonize an entire galaxy without traveling faster than light or dealing with the communication lag problems that plague direct contact. A single probe sent from one star system could reach another star using conventional propulsion that we can already imagine building, harvest resources from asteroids or comets, and construct copies of itself using those materials. Those copies would then travel to other nearby stars and repeat the process automatically, without need for ongoing communication or control from the original civilization. Within a few million years, the entire galaxy could be explored and populated by the descendants of a single original civilization. The probes would spread through the galaxy like a wave, reaching new stars at a rate determined by their travel speed and replication time. The mathematical possibility of such expansion suggests that even with present-day physics and engineering, a sufficiently advanced civilization could eventually colonize the galaxy. Yet we observe no evidence of such colonization anywhere in our cosmic neighborhood. We see no artificial structures in our solar system. We detect no probes from other civilizations visiting us. We find no evidence of megastructures being built around nearby stars. The absence of such exploration becomes profound and troubling when you consider that a civilization developing even a few 100,000 years before humanity would have had millions of years to spread throughout the galaxy. They would have reached Earth billions of years before humans evolved. They would have constructed structures throughout the solar system. The absence of evidence for such expansion is itself evidence. Either civilizations do not typically develop the technology for self-replicating probes despite having millions of years to do so, which seems unlikely given the time available and the mathematical simplicity of the concept, or civilizations that develop such technology choose not to use it for reasons we cannot fathom, or something prevents their deployment and expansion, perhaps the Great Filter itself, perhaps something that eliminates civilizations before they can accomplish this. Von Neumann probes should have filled the galaxy if advanced civilizations are common. The absence of any sign of them anywhere is perhaps the most eloquent argument for the Fermi paradox. Distance might not have prevented the spread of a sufficiently determined civilization. The absence of von Neumann probes becomes an eloquent silence. It speaks not through radio waves, but through the conspicuous absence of any sign that advanced civilizations ever attempted large-scale interstellar expansion. It is as if the galaxy is a stage where no one has ever stepped. Yet something has prevented it. That something remains unknown and haunting. It suggests that either intelligence is extraordinarily rare in the cosmos, or that something about the nature of intelligence or civilization prevents expansion, or that we are somehow missing the evidence. Something is wrong with our assumptions. The silence of von Neumann probes might be the most profound silence of all. The anthropic principle offers one philosophical resolution to the distance problem by suggesting that we exist in a universe that appears isolated precisely because we exist in it, and because only such a universe could produce observers like us. If the universe were different, if distances were smaller, or signals traveled faster, or civilizations were far more abundant and clustered together, then the universe would be unsuitable for the emergence and persistence of human consciousness. We would not be here to observe it. The universe might be chaotic, violent, constantly disturbed by neighbor civilizations waging war or competing for resources. We would not exist to contemplate these stars and wonder. By this logic, the universe we observe must appear lonely and distant, because if it did not, we would not exist to notice that it is lonely. The anthropic principle does not solve the problem of distance so much as reframe it fundamentally. It suggests that asking why the universe appears empty might be the wrong question to ask. The question should instead be, what kind of universe could possibly produce observers like us? Such a universe would necessarily appear isolated and quiet. Any other kind of universe would produce different observers, or no observers at all. An overcrowded universe, filled with civilizations in close proximity, might produce beings, but not contemplative humans wandering at stars. This principle transforms the scientific question into something closer to philosophy. It removes the emotional weight of loneliness by suggesting that isolation is inevitable for conscious observers. We observe isolation because observation requires isolation. Contemplation requires quietness. The reasoning is circular, in a way that seems both profound and unsatisfying simultaneously. It answers the question of why we find nothing by suggesting that if we did not find nothing, we would not be here as observers capable of wondering and asking the question. Yet it does not truly explain why other civilizations do not exist or why they remain distant if they do exist. It merely suggests that if they existed nearby and were attempting contact, we would not be here as lonely contemplative humans asking these questions. The anthropic principle stands as perhaps the final refuge for those hoping that the universe teems with life despite all evidence of silence. It permits one to believe in distant civilizations while accepting that we might never detect them. It allows the universe to be full of intelligence while remaining forever inaccessible to us. The principle acknowledges that distance might be so fundamental to the nature of conscious observers that no amount of technology could overcome it. We are isolated not because we are alone, but because consciousness itself emerges only in isolation. The machinery of human thought itself might shape our isolation. Future telescopes will peer deeper into the cosmos than anything we possess today, yet they will face a barrier that technology alone cannot overcome. A telescope with a mirror, 10 kilometers in diameter, far larger than any structure humanity has ever built, could theoretically resolve planetary surface details at distances of dozens of light years. But even such an instrument would struggle with objects beyond 100 light years. The fundamental physics of light diffraction creates a ceiling on what can be magnified and resolved. A civilization 10,000 light-years away could possess a megastructure so large it dwarfs Jupiter itself, yet it would appear to our most advanced future telescopes as nothing more than a point of light. The telescope as a tool has inherent limitations written into the laws of physics themselves. As wavelength of light becomes smaller and more energetic, new obstacles emerge. X-rays and gamma rays can reveal some phenomena invisible to optical light, yet they too face absorption and scattering by the interstellar medium. Radio telescopes can peer through dust clouds that obscure visible light, yet radio waves face their own decay across vast distances. Each different approach to observation reveals some features while remaining blind to others. A civilization attempting to scan the cosmos would need to deploy an entire spectrum of instruments, each sensitive to different wavelengths, each limited by different physical constraints. The most advanced future telescopes will likely achieve improvements of only 1 or 2 orders of magnitude beyond current capabilities. This might allow us to observe planets at distances of hundreds of light years instead of dozens, yet even these vast improvements would reveal only the universe within a few thousand light years of Earth, a negligible fraction of the galactic neighborhood. We would still be nearly blind to most of what exists beyond that distance. The limitation becomes not merely a function of money or engineering, but a consequence of nature itself. The universe has placed constraints on observation that no amount of technological advancement can completely overcome. Future telescopes will push these boundaries, but they cannot eliminate them. A civilization 1,000,000 light-years away would remain eternally beyond the reach of any telescope, no matter how advanced. The cosmos maintains its secrets behind barriers of distance and physics that seem deliberately designed to preserve isolation. Even if we could build perfect instruments, the universe would still hide most of itself from us. We would see only the nearest neighbors, only the brightest objects, only the phenomena that emit radiation we have learned how to detect. The invisible and the distant would remain unknown. A future SETI search might find nothing, not because the cosmos is empty, but because the portions of the cosmos we can examine are statistically negligible. We search a tiny bubble and find nothing in it, yet beyond that bubble might lie wonders and minds and civilizations that we lack the means to perceive. The detection of alien signals depends critically on how advanced those civilizations have become. A civilization at our current technological level, broadcasting with all the power we can generate, would be undetectable beyond a few dozen light years at most. But a civilization just 1,000 years more advanced might develop transmission systems that could be detected across much greater distances. A civilization 10,000 years ahead of us might broadcast across the entire galaxy, visible to any receiver tuned to the right frequencies. And a civilization truly ancient, millions or billions of years beyond our current state, might harness energies on such a vast scale that their signals would be unmistakable across cosmic voids. The Kardashev Scale provides a framework for thinking about this. A Type 1 civilization controls all the energy falling on its planet from its star, commanding power equal to our sun's entire output focused onto a single world. Humanity currently exists at about 0.73 on the Kardashev scale, nearly but not quite at Type 1 status. A Type 2 civilization harnesses the total energy output of its star itself, surrounding it with megastructures that capture photons before they disperse into empty space. A Type 3 civilization commands the energy of an entire galaxy, with access to hundreds of billions of stars worth of power. Each step represents not merely a doubling or tripling of power, but an increase by factors of billions. The energy available to Type 2 civilizations dwarfs the resources of Type 1 by amounts that make our comparisons seem almost ridiculous. A Type 2 civilization could broadcast signals across light years with power that would be impossible for us to comprehend. We have no analogy from human experience. We could not imagine having the energy to move planets or disassemble stars. Yet such capabilities would be routine for advanced civilizations. This creates a profound detection paradox. If civilizations commonly evolved to Type 2 or beyond, the galaxy should blaze with their signals. Radio telescopes should be overwhelmed with alien transmissions. Instead, we observe silence. Either such civilizations are extraordinarily rare, or they deliberately choose not to broadcast, or something prevents their emergence, or our assumptions about their behavior are fundamentally wrong. The Kardashev Scale reveals that visibility depends not on absolute distance, but on relative advancement. A Type 2 civilization to us would be visible anywhere in the galaxy. But how many Type 2 civilizations exist? Perhaps none. Perhaps only one exists in the entire observable universe. The rarity of extreme advancement might explain the silence more effectively than the vast distances between civilizations. If civilizations rarely reach even Type 1 status, then they remain invisible to everyone else, locked in silence by their own technological poverty. The thought is both humbling and chilling. We are not silent because we are alone, but because we are weak. Our broadcasts scatter into the dark, unheard beyond our solar system, not because the universe is empty, but because we lack the power to reach across the stars. Most civilizations throughout the galaxy might be equally weak, equally silent, equally invisible to their cosmic neighbors. A galaxy full of Type 0.5 civilizations would appear completely empty to anyone searching for signals. Any sufficiently advanced civilization might have learned long ago that broadcasting into the cosmos is dangerous. The dark forest hypothesis explores this possibility with unsettling clarity. The metaphor is simple yet profound. The universe is a dark forest. Each civilization is a hunter with a gun. Everyone hides from everyone else because to reveal your position is to risk annihilation. Resources are limited. Territories are vast. Any civilization that broadcasts its location advertises itself as either a threat to eliminate or a prize to claim. In a universe of potential competitors, revealing yourself is irrevocable. You cannot unsend a radio signal. Once your location is known, you cannot undo that knowledge. A civilization that broadcasts might do so with peaceful intentions, hoping to establish contact and exchange knowledge. Yet from the perspective of a distant civilization, a signal is a threat. It announces, "We exist here. We are at this technological level. We are at this location." That information could be used to plan invasion, colonization, resource extraction, or preemptive strike. The military has a concept called OPSEC, operational security. You do not reveal your capabilities or position to potential enemies. In the same way, a civilization that understands game theory and evolutionary pressure would learn that broadcasting is suicidal. Every civilization, operating independently and reasoning about its own survival, would reach the same conclusion. The universe should be filled with silent hunters, all observing, all hiding, all terrified of discovery. This theory explains the Fermi paradox without requiring that civilizations are rare or that distance is an insurmountable barrier. It requires only that civilizations are rational about their own survival and that other intelligent life might not be benevolent. If this hypothesis is correct, then the cosmic silence is not the absence of life, but the presence of it in maximum stealth mode. Millions of civilizations could exist throughout the galaxy, all of them desperately quiet, all of them scanning for threats, all of them hoping never to be found. The universe would be full of hidden minds, all of them aware of each other at some level, all of them committed to deception and distance. We might be surrounded by civilizations that know we exist, yet choose to ignore us, watching from the darkness, waiting to see if we develop weapons they should fear. Or we might be so far beneath their technological level that we simply do not matter, unworthy of even the minimal attention required to monitor our broadcasts. Either way, we would be alone in the dark, communicating into an abyss that hears us but does not answer. The isolation imposed by intentional silence might be complete and permanent. We would broadcast our location to the universe and receive only silence in return, not because there is nothing listening, but because every mind that hears us chooses not to respond. The cosmos might be full of civilizations engaged in an eternal game of mutual avoidance, terrified of contact, carefully preserving their secrets, waiting for some sign that they are not alone, yet never daring to make that sign themselves. A generation ship represents one of the few theoretical means by which a civilization could overcome the distance barriers to space travel and exploration. Unlike a conventional rocket that reaches its destination in decades or centuries, a generation ship would house entire populations across journeys lasting thousands of years. Multiple generations would be born, live, and die aboard the vessel before it reached its destination. The ship would need to be self-sufficient, maintaining its own ecosystems, growing its own food, recycling its own air and water. It would need to store or generate enough energy to power life support systems for millennia. It would need to maintain propulsion systems that could function across such timescales, or develop new ones when the original systems failed. The ship would need governance structures that could maintain order and purpose across thousands of years of travel, preventing the mission from fragmenting into chaos or abandoning its goals. A generation ship could theoretically reach Alpha Centauri in several thousand years if it accelerated to a fraction of light speed. Yet even this enormous investment would fail to bridge most of the galaxy. The distances between star systems would still require journeys lasting millennia. A civilization committed to physical expansion would need to build not one generation ship, but thousands of them, launching expeditions to nearby stars constantly, creating a wave of colonization that spread across space at glacial speeds. Yet even at these slow speeds, the entire galaxy could theoretically be colonized within a few million years, given patience and determination. The absence of any evidence of such colonization anywhere in our solar system or the nearby stellar neighborhood is troubling. If generation ships are possible, why have we not detected evidence of them? Why do we not observe megastructures or engineering projects in nearby star systems that would indicate the presence of visiting civilizations? The barrier to generation ships is not that they are physically impossible, but that they require motivations and resources that few civilizations might actually possess. A civilization comfortable on its home world might see little reason to invest the enormous resources required to send colonists to other stars. A civilization driven by philosophy or desperation might pursue such expansion, yet most might not. The distance between stars creates not just a physical barrier, but a psychological one. Millions of years separate journeys between different stellar regions. A fleet sent to neighboring stars might never hear back from the home civilization, which could collapse, change, evolve into something unrecognizable long before the ship arrives. The explorers would be cut off from their origin forever, voyaging into darkness toward an uncertain future. A generational crew might lose interest in the mission entirely after a few hundred years of journey. They might evolve culturally and philosophically into something unrecognizable from the civilization that launched them. They might forget why they were traveling at all and simply exist as a permanent space-dwelling species, never reaching their destination. Only a civilization with an extraordinary commitment to expansion and an unusual willingness to sacrifice its own citizens to impossible journeys might undertake such missions. The rarity of such civilizations might explain why generation ships do not fill the galaxy. Most species might choose stability over expansion, existence on homeworlds over desperate voyages across the dark. The cost is simply too high, the reward too distant. The sacrifices too great. The observable universe contains only a fraction of the matter and energy that must exist based on theoretical physics. Dark matter and dark energy comprise most of the universe, yet both remain almost entirely undetectable and invisible. Beyond the observable universe lies cosmic territory that light has not had time to reach us from since the Big Bang. That region may contain trillions of galaxies, each with billions of stars, yet it remains forever beyond observation. These regions exist beyond the cosmic event horizon, separated from us by distances so vast that space itself is expanding faster than light can travel the gap. We can never observe these regions, and nothing from those regions can ever reach us. This creates a profound asymmetry in knowledge. The universe is far larger than we can ever see. Civilizations might exist in regions of space that light from our galaxy could never reach. We might exist in regions that civilizations elsewhere could never observe. The observable universe might be only an infinitesimal fraction of total reality. If intelligent life is distributed randomly throughout all of reality, then the fraction of it that exists within our observable universe might be incredibly small. Perhaps no other technological civilizations exist within the observable universe at all, yet countless millions exist beyond it, entirely unknowable to us, separated by distances and the expansion of space itself. The cosmic event horizon that defines the boundary of our observable universe is expanding at the speed of light, yet it also remains roughly constant at about 46 billion light-years away. As the universe expands, new regions come into view at the distant edge of what we can observe. Yet regions beyond the horizon are permanently receding away from us, faster than light can travel toward us. It would mean that the universe beyond what we can observe is teeming with life and civilization. yet we remain profoundly alone within our bubble of observation. It would mean that the silence we observe is not because the universe is empty, but because the slice of it we can access is extraordinarily isolated. Civilizations could exist millions of light years beyond the farthest galaxies we can see, yet they would be utterly inaccessible. No signal from those regions could reach us. No spacecraft from those regions could ever arrive. We are trapped not by distance alone, but by the very structure of space-time and the finite speed of light. The universe could be full of consciousness and intelligence, yet our isolation could be complete and permanent simply because reality is larger than the light cone that contains us. We might be living in a pocket of cosmic isolation, not because we are unique, but because of the mathematical properties of an expanding universe. Infinity might be pressing down on us from all sides, full of life and minds and wonders, yet all of it beyond the horizon of what we can ever know. The emergence of intelligence might follow timescales so vast that very few civilizations exist simultaneously. A star might shine for billions of years, yet intelligent life might develop on its planets only during a narrow window of time. The evolution of life requires billions of years. The development of intelligence might require additional hundreds of millions of years. The development of technology sufficient for interstellar communication might require thousands or millions of years of advancement. And then, once technology is achieved, the civilization might persist for only a relatively brief period before either advancing to incomprehensibility or collapsing into extinction. The Great Filter might not be a single event, but a race against time. If most civilizations persist for only a few million years at a recognizable technological level, and if stars shine for billions of years, then at any given moment in time, the fraction of stars with communicative civilizations might be extraordinarily small. Two civilizations might exist at recognizable technological levels during overlapping time periods only by rare coincidence. Most civilizations might develop when their nearest neighbors are either far too primitive to contact or long extinct and vanished. The timeline of cosmic evolution might guarantee that civilizations rarely coexist. A civilization that emerges today in the galaxy might find that all other civilizations either collapsed millions of years ago or have not yet evolved. The neighboring stars might contain only ruins of ancient civilizations or breeding grounds for future ones. The coincidence of timing that would allow two civilizations to coexist at technological parity might be extraordinarily rare. Each civilization would find itself alone, not in space, but in time, the only consciousness in its stellar neighborhood to exist at a technological level, surrounded by worlds that are either too primitive or too ancient. A precursor civilization might have existed in the habitable zone around Proxima Centauri, achieving technological maturity, broadcasting into the void, and then destroying itself or evolving beyond recognition long before Earth ever formed. We arrived too late, calling out to the ghosts of ancient peoples. The cumulative effect of vast timescales and the window of technological civilization might guarantee isolation. A civilization could broadcast for millions of years and receive no response, not because it is unheard, but because no other civilization is broadcasting during the same era. The silence would reflect not the emptiness of space, but the temporal dispersion of civilizations across cosmic history. Communicating across interstellar distances might not require radio waves at all. Advanced civilizations might develop methods of signal transmission and detection that we cannot currently imagine. Perhaps they encode information into the structure of space itself using gravity waves that ripple through the fabric of space-time. Perhaps they manipulate quantum entanglement to send instantaneous signals, if such a thing is theoretically possible and not forbidden by physics. Perhaps they create wormholes or traversable shortcuts through space-time, allowing communication across distances without violating the speed of light, by moving through higher dimensions we cannot perceive. Perhaps they encode messages into cosmic microwave background radiation, or into the properties of fundamental particles. Perhaps they communicate through methods that do not involve electromagnetic radiation at all. These alternatives are largely speculative, yet they illustrate that our current focus on radio waves might be myopic. A civilization communicating through methods we cannot conceive would appear completely invisible to our current searches. We would never detect them, not because they are silent, but because we are listening for the wrong thing entirely. A sufficiently advanced civilization might develop ways to manipulate space-time itself, creating phenomena we would dismiss as natural rather than recognize as artificial. They might create structures that mimic natural cosmic phenomena so perfectly that we would never suspect intelligence. They might communicate by influencing the properties of stars or the structure of galaxies, sending messages written across space on scales so vast that we lack the perspective to recognize them as signals. We might be constantly receiving messages from distant civilizations and interpreting them as nothing more than natural phenomena, as cosmic accidents, as the boring background radiation of an empty universe. We might be surrounded by transmission channels we cannot decode, messages we cannot interpret, signals we do not have the capacity to perceive. The universe might be full of communication channels that we simply lack the intelligence to recognize. Our search for alien signals might be like an ant observing humans and trying to detect our radio broadcasts. The ant has no framework for understanding radio waves. No antenna built by ants could ever intercept our communications. Similarly, we might be utterly incapable of recognizing the signals that advanced civilizations transmit. We are not looking for a radio station that does not exist. We are looking for radio stations while not realizing that advanced civilizations transmit. We are not looking for a radio station that does not exist. We are looking for radio stations while not realizing that advanced civilizations no longer use radios. The solution to the silence might not be that no one is broadcasting, but that we are too primitive to hear. The zoo hypothesis offers another explanation, rooted in morality and ethics rather than physics or technology. The hypothesis suggests that civilizations commonly reach levels of technological advancement where they could expand to other star systems and establish contact with younger species. Yet most choose not to. They observe a policy of non-interference. They treat younger worlds like a nature preserve, keeping them isolated to allow natural development and independent evolution. A Type 2 or Type 3 civilization would have the power to observe Earth directly, monitor our civilization, perhaps even communicate with us if they chose. Yet, they choose silence because they recognize a principle. Young civilizations need to develop independently. Contact with advanced aliens would disrupt our cultural evolution, create dependency, undermine our autonomy. The ethical advanced civilization is one that watches from a distance and does not interfere. The zoo hypothesis suggests that Earth is not in a cosmic preserve, protected from contact for our own good. This would mean the silence we observe is intentional. Advanced civilizations exist, but have decided to remain hidden from us. They watch, they listen, they gather data about our development, but they do not approach. They do not answer our signals. They do not land on our world. They allow us to struggle and grow without interference, trusting that eventually we will mature enough to recognize and respect the barrier they have placed between us. If this hypothesis is correct, then contact might come only when humanity passes through some developmental threshold, some sign of maturity that the watching civilizations recognize as ready for acknowledgement. We would need to overcome our war and violence, our tendency toward self-destruction, our tribalism and cruelty. we would need to prove we are capable of peaceful coexistence even with our own species before advanced civilizations would consider introducing us to contact with theirs. Perhaps there is a great council somewhere in space, monitoring countless young civilizations, waiting for them to develop certain capabilities or certain moral understandings before extending contact. The silence in this case reflects not our isolation, but our quarantine. We are kept at distance, not because we are unworthy of contact, but because contact is not yet appropriate. We are children in a cosmic nursery, and the adults watch patiently for us to grow. This hypothesis provides a comforting thought. It suggests the silence is not permanent, that contact will eventually occur, that we are not alone, only waiting. Yet we have no way to know if this is true, or merely a wish we project onto an empty universe. Mathematical calculations suggest that intelligent civilizations should be common in the galaxy. The Drake equation, despite its uncertainties, generally produces estimates of millions of technological civilizations in the Milky Way when assumptions are even moderately optimistic. The sheer number of stars, the fraction that should have planets, the fraction of those planets in habitable zones, the probability of life arising, the probability of intelligence developing, even conservative estimates yield large numbers. Yet practical detection has revealed absolutely nothing. We search with increasingly sensitive instruments and find only silence. This creates a profound gap between what mathematics suggests should exist and what observation reveals actually exists. The possibility that the gap reflects a fundamental error in our assumptions is difficult to ignore. Perhaps technological civilizations are far rarer than the Drake equation suggests. Perhaps the barriers to intelligence are higher than we imagine. Perhaps most life never rises beyond bacterial forms. Perhaps intelligence never develops except in the most extraordinary circumstances. Perhaps we are not part of a common cosmic phenomenon, but an extraordinarily rare accident, a fluke of probability that emerged on one small world orbiting an ordinary star. The mathematical probability of our existence might be so low that finding even one other example in the observable universe would be statistically shocking. The silence might reflect not the vast distances between civilizations or the physics of communication, but the simple reality that technology is nearly impossible to achieve. Most planets might remain sterile or home to only simple life. Most civilizations might never advance beyond agricultural or industrial stages. The jump from industrial technology to electronic technology to space travel might be a barrier that very few species can overcome. Humanity succeeded only because of a particular combination of circumstances and ideas that might be extraordinarily rare. The gap between mathematical expectation and observed reality might be telling us that the assumptions behind the mathematics are profoundly wrong. The universe is far emptier than our calculations suggest, not because distances are vast or communication is difficult, but because intelligence itself is nearly impossible to achieve. The rare Earth hypothesis and the great filter might be less about a single barrier than about a cascading series of improbable events. The probability of each event multiplies. A 1% chance of life multiplied by a 1% chance of intelligence, multiplied by a 1% chance of technology, multiplied by a 1% chance of peaceful expansion, produces a 1 in a quadrillion chance overall. In a galaxy with hundreds of billions of stars, we might expect only a handful of technological civilizations. In the observable universe, perhaps only one, us. The question of whether alien civilizations are too far away to find has led us through vast distances, impossible communication delays, barriers of physics and probability, and speculations about the reasons for silence. We have considered the limitations of our telescopes, the barriers to space travel, the possible motivations of advanced civilizations, and the mathematical improbability of our own existence. What remains at the end of this inquiry is not a clear answer, but a deeper understanding of our profound isolation. The universe appears empty, not because we have looked everywhere, but because we have looked almost nowhere. The distances between stars are so vast that even our most advanced technology can barely reach across our own solar system. The galaxy is so large that our most sensitive instruments can observe only the tiniest fraction of it. The universe is so ancient that civilizations might exist millions of light years away, or millions of years in the future or past. Their existence separated from ours by barriers we cannot overcome. The possibility remains that we are alone, that intelligence is extraordinarily rare, that the emergence of a species capable of wonder and contemplation happens only once in a galaxy or once in the observable universe. If this is true, then our isolation is complete and permanent. We are the only conscious minds in our region of space and time, the only observers of this small corner of reality. We may never know if other minds exist elsewhere, never communicate with them, never learn if our form of consciousness is unique or common. Or it may be that civilizations are common, that the galaxy teems with intelligence, that countless species contemplate the stars and wonder if anyone is listening. Yet they remain invisible to us, hidden behind distances we cannot overcome, deliberately silent to protect themselves, developing according to timelines that miss ours by millions of years, or existing in regions of space we can never access. Either way, the silence teaches us something profound. It teaches that intelligence, if it is rare, is precious beyond measure. It teaches that consciousness emerging from the universe to observe itself is perhaps the most significant phenomenon in existence. And it teaches that whether we're alone or surrounded by invisible minds, our responsibility to understand, to explore, to grow, and to care for each other remains unchanged. The stars continue their ancient burning above us. The distances between them remain unchanged. And we remain here, looking up, wondering, asking the question that may never be answered. Is anyone out there? Is there another mind somewhere in the darkness that wonders about us as we wonder about them? The answer to that question may depend not on distance or detection or the existence of other minds, but on what we choose to do with the miracle of consciousness that we possess, whether we are alone or part of a vast community of minds, forever separated by space and time. The fact of our existence here, now, able to wonder and ask and search the darkness for others like ourselves, is extraordinary enough. The universe may or may not be full of life, but we are here, we exist, and that, perhaps, is what matters most.